All right. Now we want to move into trigonometric functions. The idea is quite simple. Sine, if we put in 30 degree, we got 1/2. We put in 45 degree, we got square root of 2 of 2. We put in a different angle, we can get a different trig value. Therefore, it seems like it makes sense to define something called sine x, where you put x as an angle. You produce a function value which is sine x, which gives you the trig value of the corresponding angle. This is a nice input and output question. So we actually have the definition for 6 different trig functions: sine, cosine, tangent, cotangent, secant, and cosecant, which is nice. Then we can use a calculator to start to type in, and we can see the domain range, we can see the graph, we can see all these kind of fancy things, which is very, very good. The problem with that is quite straightforward. That is, what's the domain of sine x? Now, automatically, you know, how do you define sine? Sine is defining a right triangle, which is a over c, if you put this one to be your x. Then automatically you have a restriction. How big can your angle be if you want to be in the right triangle? Your x has to be less than 90 degree. You cannot be bigger than 90 degree. For example, if I say, hey, what is sine 90 degree? You will say, let me draw the right triangle. That's the way I know how to define it. Then you draw the right triangle, you find a 90, and suddenly, boom, you don't have any triangle anymore. Kind of makes sense here. So sine 45 degree makes sense. Sine 60 degree, sine 89 degree makes sense. But sine 100 degree does not make sense if you only want to define all the trig values through a right triangle. Because right triangle, you cannot go beyond the 90 degree. Or any triangle, you cannot go beyond 180 degree. So our first job to define a function like this, we want it to be adaptable to all kinds of angles. We have to extend to trig values for any angle, not just anything between 0 and 90 degree, which is fit for a right triangle. We want something beyond the right triangle. All right, so that's our first job, trig value for any angle. Well, let's take 90 degree or 100 degree, whatever degree. Then we say we failed to draw the right triangle, of course. But we can still draw the angle, right? For example, for 100 degree, we just need to draw 90 degree and then another one, 10 degree. This is 100 degree. That's what we got from 5.1, how to draw an angle. It's in quadrant 2. Okay. Now, how do we define the trigonometry value, which means sine, cosine, tangent, cotangent value for this angle? So the first one, we know how to draw the angle. It's in a quadrant. Second, well, the definition should be consistent with what we had before. Right? So how do we define sine and cosine for this? Then we extend it to say, hey, how do we define sine and cosine if it's not in quadrant 1? It's somewhere here. So first, what you want to do is, you want to draw the right triangle. You can draw this right triangle, you can draw this right triangle, and as we said, if you're just talking about this angle here, which triangle you draw really doesn't matter. A bigger one, a smaller one, they share the same ratio, right? Okay, so just draw one. Right. Once you draw this, because you're in a coordinate system, naturally, you will have a coordinate x and y for the point. Okay. Then you will know this is your y, and this is your x. Moreover, you do know this r, which is the hypotenuse, which is given by square root of x squared plus y squared. Then, through the definition before, for this theta, we can still do the same definition, but this time using the sides based on this point. Sine theta is y over r. Cosine theta is x over r. Cosecant, right away, r over y. Secant, r over x. Tangent, y over x. Cotangent, x over y. So automatically we can have this definition. Note, what do we need for this definition? We just need a point. All right. Now, if you go beyond the right triangles, you have something here. What do you have? Number one, you do not have a right triangle anymore because this angle goes like this. It's way beyond the right triangle. Second, do you still have this point xy? The answer is yes. Can you still calculate r? If you know x and y, of course I can calculate r. Then, this definition, you have x, you have y, you have r, this definition will still work, even though this angle is not in the right triangle anymore. The difference is, now you can have something which is negative, because your x and y can be positive or negative, depends on which quadrant you are in. Okay, so this is the extension of the definition of trigonometries. Instead of going into the right triangle, which will always be positive for all the three sides, which only works for 0 to 90 degrees. Instead, what we do is, we have an angle, and we know how to draw the angle, which doesn't have to be in quadrant 1. Great. Once you know the angle, we can pick a point on this angle, which is called x and y. Okay. Once you know x and y, what can you do? You can actually calculate r. Then with that, you can always define trig value in x, y, and r, depending on which one you are looking for. Moreover, the choice of x and y does not depend on how you pick it. As long as it's on the terminal side, you pick this one, you pick this one, you pick this one. As far as we are concerned, their trig values stay the same because you're talking about the ratio here. All right. So now let's go back to some examples. Number one, what is sine 90 degree? Which you cannot do before. But now what you do is, this is 90. Pick a point. You can pick 0, 1. You can also pick 0, 2. Doesn't really matter. Okay. After that, what do? You define sine 90 degree, which is going to be y over r. Okay. Now you just need r. Going from 0, 1, r equals square root of x squared plus y squared, which is 1. So this is going to be 1 over 1, which is 1. So sine 90 degree is 1. What if you pick the 0, 2? Then your r is going to be square root of 0 squared plus 2 squared, which is 2. So your sine 90 degree is going to be 2 over 2, which is also 1. So from here you can see pick 0, 1, 0, 2 doesn't really matter. This is something we cannot do before because it's not in a right triangle, but now we can do it. What is cosine 180 degree? Try that. Where is 180? Here is 180. Let's pick a point. Negative 1, 0. Again, negative 2, 0 will also work. Okay. So cosine equals x over r. X equals negative 1. R equals, so. Now, draw the coordinate system and see any kind of angle. Can you always find a point? The answer is yes. Once you find the point, you have x and y. Once you find x, y, you can calculate r. So you can define all the trigonometric values, no matter which angle you put in. That is the beauty of the trig function. So, this definition will work for any angle. not just the ones in the right triangle, but also the ones beyond the right triangle. You can even put a negative angle there because you can have a point there, so everything is fine. All right. Nice. Now we have the 6 trig values. Now they actually has been upgraded to functions. Later, we will be talking about the domain and the range of them. We will be talking about the graph of them. And nicely, sine and cosine will become waves like this. So that will be the foundations of everything we will be talking about for the rest of the semester. But for now, this is the first time we have seen it. All right. Now the second thing is, of course, we want a quick way to extend our method to find the trig values, okay, of any angle. So evaluating the trig values. Okay. What do we have? We know the trig value for any right triangle. Okay. Number 2, we want something beyond the right triangle. I can show you all this kind of method can be decomposed into 2 parts. The first part is trying to find the value. The second part is try to find the sine. And let me explain what I mean. Okay, this is easy. You draw it. Okay, you have a right triangle. If you put a 20 degree here or 30 degree here, you will be able to draw this. Or you can use a table to find what the value is. So this is done. We know how to do it. What we worry about is when the angle is not in quadrant 1. For example, when the angle is here. But now if you take a closer look, do you still have a right triangle? The answer is yes. I still have a triangle. So can you still do everything we had before? For example, if we have a 30 degree here, you can still do 1 square root 3 of 2. So you can do everything we have done before for this right triangle. The only difference is if you are thinking about the cosine of this angle, which is going to be x over r, which you can see is the same as the right triangles before, except your x is less than 0. So the whole cosine of this thing is negative. Sounds good? So for all the new angles we have now, no matter it's in quadrant 1, quadrant 2, or quadrant 3, all we need to do is, number 1, try to find the value, which is always positive, by focusing on this right triangle here. Second, depending on which quadrant you have, you will need to determine, are you positive or are you negative? Because if you're 1/2 before, you're still 1/2 now. It's just you may have a possibility that you can be positive or negative 1/2. Sounds good? Okay, so with that idea in mind, let's do them one by one. The first one is how to find the value. That means even though you don't have a right triangle, can you find a right triangle for the values? The answer is yes. How do you do that? Through something called a reference angle. That is, even though I may have something like this, I can still form a right triangles no matter which quadrant you are in. And then I have a right triangle. And the answer is quite easy. We just pick the angle between this one and the x-axis. So no matter which quadrant you are in, this reference angle will be always between 0 and the 90 degree. Therefore, we can put it into the right triangle. So we call it theta bar. Now, for example, if you have an angle which is tangent 300 degree, what do? You draw 300. Then you realize the reference angle is going to be this. Through some calculation, this is 360, this is 300, so it's going to be 60 degree. So in order to find tangent 300 degree, you just do the tangent 60 degree instead. which is square root of 3, which we already know. The only problem is this one can be positive or negative, because now your x and y can be positive or negative, which naturally lead to the second part. That is, how do you know something is positive or negative? The sign. Not the sine, cosine, sine, but the sign of positive or negative. How do you know that? Well, let's look at the definition. Sine data. It is positive or negative. Well, check r, which is square root of x squared plus y squared. Can you see r is always positive? Okay. Then is this one positive or negative? It really depends on, is y positive or negative? Right? Now if you put everything into the quadrant, do you know how to draw y bigger than 0? That's everything above the x-axis and everything below. So for sine, we can easily have a graph to tell us it really depends on which quadrant you falls in. If you're talking about this angle, the sine is positive. If you're talking about this angle, the sine is negative. Okay, if you're talking about positive, this angle, negative, this angle, negative. So it really depends on which quadrant you falls in. That will be super convenient. So this will be the graph for sine. And of course, it will be the graph of cosecant. Because if you take the reciprocal, what's positive, stay positive. What's negative, stay negative. Similarly for cosine, you can think about it. I'm going to skip it by the definition. This works for cosine. Therefore, it works for secant. Finally, this is one works for tangent and cotangent. So what sign do you want? Well, it really depends on which quadrant you are in and also which trig identities. So I know which graph I should look at. Now back to the question, let's see the example. Find a tangent 300 degree. Okay, what do we do? Step 1, we draw 300. Step 2, we figure out theta bar equals 60 degree. So instead of doing 300, I should do 60. The last step, try to determine positive or negative. Now for tangent, we have the 3 graphs. Draw this. Quadrant 4 for tangent, it's going to be the negative. So tangent 300 degree equals this, which is a combination of the right triangle before, plus how do we figure out the sine. All right, let's try some other examples. Example. Cosine 200 degree. If this is 180, you can know this is 20. So this is the same as cosine 20. Positive or negative for cosine, draw the graph. It's going to be negative. Final question, what is cosine 20 degree? Well, it's not one of the special angles, but we can actually use our table or a calculator to figure it out. From here, knowing every trig values from 0 to 90 degree, you will be able to extend it to any angle if you just figure out what sine it is. Let's try one more. Let's do tangent. We have done tangent before. Let's do cosecant. 735 degree. 935 degree. First step, let's try to draw it. 935 minus 720 degree. which is 2 complete cycle. We have 215. 215, if this is 180, 215 is roughly here. So 935 is also going to be here. Okay. The value here is going to be 215 minus 180, which is 35 degrees. So number 1, I find the reference angle is cosecant 35 degrees, which is 1 over sine 35 degrees. Positive or negative for cosecant, which is sine, it's going to be negative. Now, if you have a calculator, negative 1.74. Okay, usually we won't have some angle as big as this. You can plug it into the calculator directly, but this is actually how the calculator does it. So you only need to know all the trig values for everything from 0 to 90 degrees. Anything beyond that, you draw the graph to figure out what's going on. Okay. Note, two coterminal angles have exactly the same trig values. That means if you have two angles, let's take one angle, which is 30 degrees. Let's take another angle, which is 390 degrees. Okay, there are different angles. One goes like this, the other one goes like this. Hold on. Okay, one goes like this, the other one goes like this. However, they are coterminal angles, which means they share the same terminal side. If they share the same terminal side, they share the same point xy. Then they share the same x over r, y over r, same all the trig values, because they have the same x, same y, and same r. So even though for different angles, they can share the same trig value, as long as they're coterminal, which means the difference between them is a multiple of a complete cycle, which is 2 pi. Okay. It's just some side topic. So, for your record, try to find the following values without using a calculator because we are using special angles. Sine 7 pi over 3. Remember, it's related to pi over 3, which is 60 degrees. Try to find cosine 5 pi over 6. Try to find tangent 7 pi over 4. We will go over just one of them. Okay, this is pi. This is 5 pi over 6. So this is pi over 6. But remember, it's 30 degrees. You want a cosine. So cosine 5 pi over 6 is the same as cosine pi over 6, because that's my reference angle. Moreover, cosine negative. So together. Okay? I think that's enough examples for in class. Try some examples by yourself. Your job is to try to reflect this one really, really quickly. Okay? Try some examples with pi over 3, pi over 4, and pi over 6, corresponding to 30 degrees, 45 degrees, and 60 degrees. Because these are the special ones we can really quickly try to play with to see what's going on for the new concept. Okay? That's what we do. And of course, finally, we have one more thing to worry about. That is when you don't have a right triangle, no matter how you draw it. Right triangle, no problem. So the only part you get confused will be here, 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 and here. On these four axes, really, you do not have any right triangles, no matter how you draw it. Your reference angle is going to be 90 degrees. Okay. But the good news is actually they are the easier case. You can simply draw it. So try your best to write down the sine, cosine for all these four angles. I will start with one. Sine, cosine. Let's use, actually let me try this one to make it not standard. Sine pi over 2, cosine pi over 2, okay, tangent pi over 2. Since we don't have a right triangle, we just need to do this. Which is actually easier, because if it's pi over 2, we can simply pick a point, 0, 1, which implies r equals 1. So this is going to be y over x, which is, note, this is undefined because you're dividing by 0. So for tangent, we do have some cases where when we divide by x, if your x is 0, it's undefined. Similarly, reciprocal, then undefined. That's everything we have for pi over 2. Your job, try 0, pi, and 3 pi over 2. Using the same logic, because for these ones, we don't have a nice right triangle, even if we refer to the reference angles. But actually, they're easier to handle. All right. The third thing, maybe you have already noticed, we do have 6 trig values. But the problem is, if you know sine, you know cosecant automatically. If you know cosine, you know secant automatically. So by reciprocal identity, even though you have 6 trig values, but really you just need 3. The other 3, just flip the first 3. You will be fine. That's the beauty of the trig identity. Knowing the identity, you can memorize less. And the first one are the reciprocals. That is, sine and the cosecant are reciprocal of each other. Cosine and the secant are reciprocal, and the tangent and the cotangent are reciprocals of each other. That means if you have sine, you have cosine, you have tangent, it seems like you have 6, but really knowing the first 3, you don't have to know these 3, because you can get it from the first 3. That is nice. Now let's go further. Let's use theta instead, actually. Remember the definition, which is this. And you know sine theta equals y over r, and cosine theta equals x over r. So you can easily see if you take this over that, r and r cancel each other, you will have tangent theta, which means tangent theta is not standing alone, because if you take sine over cosine, you will get tangent. So all these implies 2 additional reciprocal identities. You take sine over cosine, you have 1 over r divided by x over r, which is y over r times r over x, which is y over x, which is exactly tangent. You can verify by yourself. Okay. Similarly, cotangent. That means even for tangent, you don't actually have to know it. because knowing sine and cosine, you know tangent. Knowing sine, cosine, tangent, you flip every single one of them, you know all the rest. So it seems like you have 6 trig value, but really, you only have 2. Or, can you even do better? Can you get cosine from sine, or can you get sine from cosine? Because if you can do that, all you really need is just 1 trig value, and that's it. Because knowing 1, you can get the other 5. Through some process, of course. Can we? The answer is yes. We have some other identities, which are called the Pythagorean identities. I will just do the right triangle example to show you why. All right. The first one is sine theta squared plus cosine theta squared equal 1. The second and the third. Memorize these 3, especially the first 2. They are very, very important. Why are they true? I can show you the proof of the first one. What is sine theta? A over c. Cosine theta, b over c. Now let's do the computation. And they have the common denominator, so we can put them together. The identity tells you this is 1. That must mean the thing on the top is going to be c squared, because c squared over c squared is 1. That implies a squared plus b squared must be c squared for the identity to be true. The problem is, does a squared plus b squared equal c squared? If you have a right triangle, yes, because it's the Pythagorean theorem. Therefore, the first identity is true because of this simple fact of Pythagorean theorem. Exercise to do the second one. Again, using the Pythagorean theorem somewhere, you will be able to show tangent square plus 1 equals secant square. All right. So let's wrap up what we have. Knowing sine, you can find cosine using the trig identity because they squared sum together equals 1. Knowing sine and cosine, you can find tangent. Knowing these 3, flip them, you will be able to find cosecant, secant, and cotangent. So this basically implies knowing 1 trig, you can find the other 5. You really don't have to know all the 6, or even 3 or 2 of them. You just need to know 1. Then you can find the rest. All right? So let me show you some examples. I will show you 2 ways of doing it. One way using right triangle, and the other way using trig identities. Okay? So let's say we know tangent theta equals 2/3. Okay? And we know theta is in quadrant 2. Actually not 2, 3. Find all the trig values. You have 6. You only know 1, so you need to find the other 5. How do you do that? You do it by using the trig identity. Okay. The first way to do it, we use the right triangle. You have tan and theta. Okay. You have 2 and 3. Then, by Pythagorean theorem, this is going to be square root of 13. Once you have that, you have all the 6 trig values. With only one problem. That is, theta is in quadrant 3. So technically, whenever you draw a right triangle, what you're drawing is not theta, but theta bar, the reference angle, which only tells you the right value with no problem, but they cannot tell you the positive or negative. So how do you do that? You do it by drawing the graph. For sine, therefore it's negative if it's in quadrant 3. For cosine, negative. For tangent, you already know it's 2/3, positive. It's given by the problem. Or it's in quadrant 3. You can easily draw it. So you need to adjust, but only for the sine. So this is the first way to do it. We do it with the right triangle, but just keeping one thing in mind. That is, what you draw in the right triangle is not theta, but the reference angle theta. The good news is the values will stay the same. You just have to add positive or negative in the end, using the information here. All right, that's the first way of doing it. Second, how do we do it? We use trig identity. Now go to the trig identity table you just write down. You have sine squared plus cosine squared equals 1. You have tangent squared plus 1 equals secant squared. You have cosecant and cotangent. Which one do you want to use? Of course, this one. Okay, that one involves tangent. So step 1, you have secant theta equals this, which is this, with only one problem. Luckily, you know theta is in quadrant 3. This works for cosine and secant, then you know you should take this one. So that's step 1. Four more to go. Once you know secant, good news is automatically you know cosine. Okay, so we have 1, we have 2, we have 3, 3 more to go. Of course, this one also gave you cotangent. So 2 more to go. They are sine and cosecant. Now you know you just need to know one of them because the other one is the reciprocal. How do you do that? That's where we use the identity. Tangent. Right. And we do know tangent. We do know sine, cosine. Then cosecant. So we finished. Same way as we did before, same number as we did before, but a different approach, using purely algebra. There's no graph, no anything involved, no right triangles, purely just trig identities. Which one is better? For this problem, the right triangle is probably faster. Okay. But later, when you get something more complicated, it will be frustrated for you to write down right triangles, especially when you have multiple right triangles involved. But you can always trust trig identity, okay? Because it's purely algebra. There's no geometry involved. Personally, for me, I would suggest for now, try both every single time. And in the exam, just write down either one. Unless I request you to do in a specific way. Either one, I will take them. Okay? The key is pay attention to the values and pay attention to positive or negative sign. Because all the trig identities before we had, they involve the square. So you need to take the square root. And when you take the square root, as you did here, you have positive and negative cases. All right. More exercises on the way, but I think that's enough for the lecture. The last one is just a simple formula. Which is a quick formula for the area of a triangle. Which, by the way, doesn't have to be a right triangle. Let me draw any random triangles. Okay, here's the key. For any triangle, and you are looking for the area, suppose you already know two sides and the angle between them. Okay. Then the area can be calculated using this formula. You could memorize this, or you can simply draw a triangle every time and derive the formula by yourself, which is quite simple, by the way. What's the area? Base times height. What is height? Height is this. Okay. Now you know the relationship. The height is in the right triangle. And it's not hard to see. Sine theta equals h over a. Therefore, h equals a times sine theta. Now if I plug this one back in, h, and replace h by this, you have the formula we had before. Okay, so you can either memorize this or you can just go through this process. Skip the hassle of memorizing, but just do a right triangle every single time. It's your call. So quick example, very easy to see. If you have a triangle like that, you have 2 and 3, you have 30, and the area equals 1/2 times 2 times 3 times sine 30 degrees. Very quick, okay? But the hidden assumption is you actually went through finding what the height is using trigonometries. Okay, note. Make sure the two sides and the angle is between the two sides. So if you know this, you cannot use the formula, because for the formula you need the angle between these two sides. So cannot use the formula directly. Instead, find theta first. The angle has to be very specific. It has to be the angle between the two sides. This angle doesn't work, this angle doesn't work. Unless you spend some additional time to figure out what this angle is. All right, that's all for trig functions, the first